You know, when you see the words eat, MT, your brain instantly gets that they're related, right? But for a computer, that's a whole different story. It's actually a classic programming puzzle. So today, we're going to crack the code on how to group anagrams and explore the really clever thinking that makes it all work. Okay, so take a look at this list right here. Seems pretty random, doesn't it? But there's a pattern. There are little groups of words hiding in there that share a secret. And that's the real question, isn't it? How in the world do you get a computer to see those connections and group them all up automatically? And that secret, of course, is that they're anagrams. You probably already know this, but an anagram is just a word you can make by scrambling up the letters of another word. Think about it. Eat, tea, and ate. They all use the exact same letters. That's what makes them a family, a group. Now, this isn't just some fun little word puzzle. This is a problem you'll actually see in software development. Imagine someone hands you this gigantic, messy list of words, maybe thousands of them, and says, go find all the anagrams. Seriously, where do you even begin with that? And right there, that's the heart of the challenge. Our brains are amazing pattern matchers. We see eat and ate, and we just get it. But a computer, it just sees a sequence of letters. To the machine, EAT and ATE are as different as night and day. It has zero concept that they're made of the same fundamental building blocks. So the solution to this is actually really elegant. You could try the brute force way, comparing every single word with every other word, but that would be a nightmare. No, the key insight is to ask, what if we could create a unique signature, like a fingerprint, a special code that would be exactly the same for every single word in an anagram group? This right here is the big idea. We need one single consistent way to represent these words. The fancy term is a canonical representation, but just think of it as a secret key. If we can figure out a way to process eat, tea, and ate and make them all spit out the exact same key, then the problem basically solves itself. We just throw everything with the same key into the same bucket.
Okay, so how do we actually make this signature? Well, the first method is just beautifully simple. It's something we've all known how to do since we were kids. We're going to use good old alphabetical order.
Here's how it works. It's super straightforward. Let's take the word eat. You break it down into its letters. E, A, T. Now just sort them alphabetically. What do you get? You get 8, right? Now for the cool part, what happens when you do the same thing with T? You get 8. And 8, you guessed it, 8 again. That sorted string 8, that's our unique signature. And what you end up with is this perfectly organized system. Think of it like a dictionary or a hash table if you're a coder. The key is our sorted signature, like AT, and the value is the list of all the words that made that key. So ant and gnat both create the key, ant, so they go in a bucket together. Bat creates ABT and gets its own bucket. Boom! Just like that, everything's perfectly grouped. It's so clean. So sorting works. It's great. But in programming, you always have to ask, is there a better way? Is there a faster way? Turns out, there is. Let's look at a totally different way to build our signature, this time using a little bit of counting. Let's back up and ask a more fundamental question. What is an anagram, really? At its core, it's just a word that has the exact same number of each letters as another word. So, what if we just ignore sorting altogether and build our signature based on that count? It's actually pretty simple. For a word like tea, the count is just 1A, 1E, and 1T. And, 0 of everything else. This count, this specific profile, becomes a unique fingerprint for that set of letters, no matter what order they're in. So this character count becomes our new key. You could represent it as a list of 26 numbers, one for each letter of the alphabet. And just like with sorting, any word, tea, eat, or ate, is going to produce the exact same list of counts. And once again, we use that signature as our key to group everything up. Okay, so now we've got two great methods. Both of them work, both give us the right answer, but in programming, it works is only the first step. The next question is always, how fast does it work? It's all about efficiency. So let's put these two head to head. Sorting versus counting. Which one is the champion? You've got the sorting method, which is really intuitive and easy to understand. And then you've got the counting method, which is a bit more clever. But when you're not dealing with 6 words, but maybe 6 million words, which one is going to come out on top? This is where efficiency is everything. Let's find out. All right, let's get into the nitty-gritty of performance.
If we have n words and the longest word has k letters, the sorting method speed is described as n times k log k. Now that k log k part, that's the price you pay for sorting each word. It's not free. But now look at the counting method. Its speed, just n times k. We just go through each letter one time to count it up. See what happened? That extra expensive log k factor, it's just gone.
And that's the punchline, really. Because the counting method completely avoids that sorting step for every single word, it's generally going to be faster. You're swapping out a pretty intensive sorting process for a super simple one-pass count. And when you're dealing with really long words, that difference isn't just small, it can be absolutely huge.
So let's boil it all down. What are the big takeaways here? Number one, the whole secret to this problem is the signature. Find a way to create a unique key for each anagram group. Number two, sorting a string is a perfectly good, easy-to-understand way to create that signature. And number three, if you really care about speed and performance, creating a signature by counting the characters is the way to go. And that's pretty much it. But I want to leave you with this one last thought. This idea of creating a unique signature, it's way bigger than just grouping anagrams. It's an incredibly powerful tool in a programmer's toolbox. So think about it. What other kinds of problems out there could you solve by finding a clever way to create a unique fingerprint for something? Whether it's duplicate files, images,